Okay, I know this has been a very long module, so let's close it up here with a collection of ideas. First, what are the Matlab functions? Well, trapz will do fixed trapezoidal approximation with data arguments x and y represents f of x, and the x data can be irregularly spaced. It simply adds up the areas of all the trapezoids under that graph. Integral does the adaptive Simpson's method, much like the ARSimp that I showed in our code. Its input arguments are a function handle, and the function should be vectorized, as well as the interval endpoints and a stopping tolerance. There are really no functions for the derivative. There's the diff function, which we used to take successive differences between a vector, and that's about it. Otherwise, you have to build it yourself. Where can you learn more about this? More error analysis, improved algorithms, multidimensional integrals, partial derivatives, and so on can be learned in Math 128A and B. I encourage you to pursue that if this interests you. Now, what are some other alternatives for differentiation beyond just the finite differences, even at intermediate values, let's say, when only finite samples are available? One, you can use regression with differentiable basis functions, and after computing the regression function, just calculates its derivative, either analytically or perhaps using the finite difference methods. This can be especially useful when the data is known to be corrupted with measurement errors, where the function relating x and y is actually much smoother than the data indicates. Regression will reduce the confounding effect of this noise, and the derivative of the regression function may represent the underlying derivative that you're looking for. You can also use interpolation, as I mentioned, and estimate the derivative by taking the derivative of the interpolating function. Those higher order formulae which we looked at are exactly derived in that manner. Of course, you could also use cubic splines. They have continuous first and second derivatives, so they may be useful in this manner as well. Another viewpoint on all of this, both numerical integration and numerical differentiation, is something called estimation. Often a system of some sort, maybe it's a physical system, maybe an economic system, maybe a biological system, is producing the function and data that you're looking at. And the system has a particular complexity inherent to itself. There may be some prior knowledge limiting this complexity. For instance, you might know the derivative will never exceed plus or minus 5. Or the derivative is usually positive, something increasing. Let's say the GDP of a country typically goes up each year. But occasionally it can be negative. Or on the average, the derivative is nearly zero over some window that you understand. There's unknowns, of course, that exacerbate the problem. The function evaluations might only be available at discrete values. We've looked at that. And the behavior of the function in between these points is not exactly known, but this prior information that I'm mentioning up above may be very informative in that sense. The other thing is the function evaluations may be inaccurate. There may be additive, like we looked at, measurement noise, which corrupts each measurement or each evaluation. Prior knowledge about this noise and how it's entering may enable you to make clever guesses as to how to eliminate it. Estimation theory is a branch of mathematics and engineering that addresses these types of questions. Given a system whose response or evolution is driven by external influences and whose measurements are corrupted by external influences, how do you get optimal estimates of the internal signals within the system? And that's an interesting thing to pursue, and if you have a chance, take some advanced undergraduate or graduate courses on estimation theory. All right, that closes the module. Good luck with the homework.